Okay, welcome back. So, in the second part, we will look at measurement fundamentals, right? So, as I may have mentioned, um, measurements are very important in testing, right? So, remember what test does, right? Suppose I have a circuit and let us say this is an output pin, right? When I apply some inputs, right, a good circuit produces some output. Let us say it produces logic 1. Okay. If it is a digital circuit, the good circuit, let us say, produces a logic 1, right. On the other hand, suppose the circuit has a fault, okay, it has some manufacturing defect, because of which the faulty circuit produces a different value, let us say logic 0, right. So, this is for a digital circuit. Now, how do you check whether the output is a logic 1 or a logic 0, right? So, you have to measure the voltage here at the output. Okay. So, that emphasizes the importance of measurement, right. In the same way, if the circuit is an analog circuit, and if I apply some input, okay, so maybe it is supposed to produce a sinusoidal output, okay, and maybe its amplitude is some value, right, and maybe its frequency is some value. Because of some defect, okay, some parametric defect, okay, or parametric fault, the sinusoidal that is getting generated may have a different amplitude, or it may have a different frequency than what a good circuit will produce. Or if there is a catastrophic fault, right, then the output may be completely different. It may saturate to some value, it may produce a DC value of whatever VCC was, right. If the VCC is 15 volts and minus 15 volts, right. So, the output may not even show a sinusoidal, it may show you something close to 15 volts or something close to minus 15 volts. So, the output is very different from what is expected, right. So, we should be able to measure the waveform parameters like frequency, amplitude, etc., right. So, measurement is an integral part of testing, and it is good to know how to use some of these equipment, right. Actual test equipment is somewhat expensive, right. I have told you that automatic test equipment which is used in the industry tends to be very expensive, of the order of millions of dollars. But in the college labs, you may find simpler measurement equipment. For example, you may find things like oscilloscopes, right. You may find things like multimeters. Okay. A more well equipped lab may also have things like spectrum analyzers, logic analyzers, and so on, right. So, we will not have time to go through all of the equipment, but it is good to sort of know little bit about measurement. Okay. the first and foremost thing to understand is a measurement can have an error, right. When I measure some value, suppose I measure the voltage at some node, let us say n. Suppose I measure the voltage as 2.848 volts, okay. Whether it is really 2.848 volts, it may be slightly higher than this, slightly lower than this, right. So, there is some error always, okay. In chemistry lab, in the first year of engineering, students go to the chemistry lab, right. Sometimes they have to prepare a solution and they have to weigh exactly 50 milligrams of some compound, okay. And there you are taught how to use that physical balance and make a very accurate measurement of that 50 milligrams of the chemical, right. So, and you will realize that a lot of precautions will have to be taken to make sure that it is exactly 50 milligrams, right. Even then there may be some scope for error. So, if there is an error, okay, suppose I measure the output of the circuit, right, and let us say the good circuit produces a logic 1 and a faulty circuit produces a logic 0. Okay. Now, remember how logic 0 and logic 1 work, right. So, this is my VDD, this is my 0. So, in digital logic, there is a margin, right. So, this area is considered logic 1 and this area is called logic 0, okay. And everything in between is neither logic 0 nor logic 1, okay. So, when you make the measurement, right, suppose because of error of the measurement you confuse a logic 1 to a logic 0 or a logic 0 to a logic 1, then two things can occur, right. You were supposed to read the output as a logic 1, but you read it as logic 0, right, and you will declare that it is a bad circuit, right. So, that is called as a false failure. The circuit did not have any problem as such, it did produce a logic 1, but it was a little bit somewhere here maybe, okay, and your measurement showed you that it is more towards logic 0, okay. You measured there was an error and you concluded that it is a logic 0, and as a result you will consider this to be a logic a faulty device. It can also be a type 2 error, right, where you may end up accepting a bad device, it is a false pass. So, you were supposed to read the output as logic 0, but due to measurement error you read it as logic 1, okay. The circuit may have produced this value and because of measurement error you may have read something above and you concluded that it is a logic 1, but indeed it was logic 0, okay. So, remember what testing does. I have told you that in the manufacturing line you get lot of these chips, right. It could be chips or it could be PCBs, it could be complete products, okay. We have manufactured a large number of them and we are individually going and testing each one of these, right. And let us write down a table like this. So, the device is good and the device is faulty. These are the two things that can occur. So, when I pick up one of these devices for testing, it is possible that it is a good device or it is a faulty device, and this is what test results show. Test concludes device is good, test concludes device is bad. Okay. So, you see this is all right, the device is good and the test also concludes that the device is good. So, this is a good situation to be in. Okay. Similarly, if the device is faulty and the circuit declares that it is faulty, this is also okay. Okay. Both these are acceptable. So, this is what is a type 1 error. That means the device is good, but the test concluded that it is a faulty device. Okay. So, this is a false negative. Okay. Whereas here, I am sorry, this is a false positive. Okay. Whereas here it is a false negative. That means the device is actually faulty, but your test is accepting that device. So, this is a type 2 error. What is the problem with type 1? Type 1 error leads to what is called as yield loss. Okay. You are rejecting good devices, okay, and as a result your profitability is getting affected. Okay. So, company makes losses. Okay. Remember I told you about binning, right? I told you that it is not just go and no go. Sometimes we may have several bins. So, this is a reject bin, it is a bad chip. This is a bin where chips work at 550 megahertz. This is 500 megahertz and this is 450 megahertz, and maybe there is another bin where it is less than 450 megahertz. Okay. So, if I have categorized them like this, right, yield loss can also occur because you wrongly put a chip which would have worked at 550 into this bin. Okay. It actually can get you a higher price, okay, but because the test made an error, you categorized it in the wrong bin. Similarly, if it could work at 500, but you categorized it as a lower bin. This is similar to, see, at the end of every class when an exam is conducted, all of you get grades, right? You get A plus, then A, right, A minus, okay, and finally F. Okay. So, there are many grades that can be awarded to you. There is always a little bit of gray area, right, whether the student is an A or A minus or an A or an A plus. So, when we write down the grades, right, it is possible that we misclassify. Okay. Sometimes the student gets lucky, and even though he is an A minus student, he may become an A, or sometimes he becomes unlucky, and even though he is an A, he gets classified as A minus, things like that. Okay. So, type 1 error is when the student became unlucky. Okay. He deserved an A, but he is getting categorized as A minus. Okay. Type 2 is just the opposite. That is, the student is lucky. Okay. So, he probably deserved a B minus, but he ends up getting a slightly higher grade. Okay. In an extreme case, the student really deserved B minus or something, but he ends up getting an A. Okay. That is an error in the testing process. Okay. So, if you look at the examination, okay, this is the portions that were covered. This is the portions or the syllabus that was covered. Okay. this student really studied only a part of it, okay. And he lucked out because the teacher decided to ask most of the questions from this part, okay. The test did not really cover all these other things, right. The student became lucky and he got an A or A minus, okay. Whereas if the student, so that is why coverage is very important, okay. We have to ask questions such that all the concepts that we taught in the class are covered in the examination. Such a test paper is unlikely to create these kind of type 1 or type 2 errors, right. In the same way, if I get a circuit for testing, I must apply sufficient number of tests so as to expose every possible fault, okay. So then we say the test coverage is good, okay, or fault coverage is good, okay. So just like in your question paper, if the concepts for every concept that was covered in the class, suppose the question that you have asked, maybe there is one question which covers these concepts. So let us say these are the concepts that were covered in the class. So one question covers all these, okay. If a person answers that question correctly, that means he is familiar with these concepts. There may be another question which covers these concepts, and a third question that covers these concepts, etc. So if I end up covering every concept, then that's a good question paper, okay. But if I leave out a few concepts, okay, then the student may come out without knowing those question papers, okay. See, in some universities they have answer any 5 questions out of 8, okay. See, that is definitely going to cause these kind of problems, okay. So the students tend to prepare for only 5 of the questions and they may pass, in fact they may get a high grade, but they have left out preparing for many of these other concepts, and they may become important in the future semesters, and that may lead to difficulties and so on, right. So I hope everybody understood the difference between the 4 cases, right. A good device being classified as a good device, a good device being classified as a bad device, that is type 2 error, I am sorry, type 1 error, a bad device being classified as a good device, that is type 2 error, and of course a bad device being correctly classified as a bad device. A type 2 error is also sometimes called as a test escape. That means the faulty device escaped the test and got classified as a good device, right, and that leads to loss in quality, right. It leads to poor DPM, okay. You sold a certain number of chips to the customer as good chips, but actually they had some faults in them. So the customer will discover those faults and point them out. So the number of defective parts per million, as far as your calculation is concerned, maybe it was 200, but the customer is telling you that actually you supplied 250, okay. So that can lead to difficulties, right. So that is what you have to understand. Now, what are the sources of measurement errors? Why do measurements sometimes have errors, okay. One source is called as random error, okay. If you have used especially analog readouts, okay, you may have used analog ammeters, okay. So they usually look like this. There is a sort of readings of the current, right, and there is a needle that tells you what is the current, etc. So, when you read out, you may make a mistake. Okay, human parallax error could be there. It depends on which angle you are looking at the this needle, right. So, parallax error etc. can lead to such wrong errors, and they are called random errors because error can be either in either direction. If you ask 10 different people to read the analog value, the actual value may be 2.5 amperes. Some people will read it as 2.4, some people will read it as 2.5, some people will read it as 2.6. Okay. So, it will be like a some sort of a distribution like this. 2.5 is the sort of average, right, and some people will actually read the lower values and some people. So, that is why it is random. So, if you read the same reading multiple times, see, you may have wondered why sometimes you are asked to take multiple readings, isn't it? When your teachers ask you to do a lab experiment, they ask you to read multiple times, okay, the same if you have done the experiment of an oscillator or amplifier or whatever, then you will be asked to read multiple times. In fact, if the group has 4 people in the team, then each person is asked to read, and some people will read high, some people will read low, but if you average it out, the chances are that the result will cancel out the errors and you may get the correct answer. Okay. So, that is why it is a random error, whereas sometimes there may be a systematic error or systemic error. Okay. Some people also call it as a systemic error. So, for example, the meter has not been calibrated correctly. Okay. So, how do you calibrate the ammeter? If you happen to know that there is a 1 ampere current in a particular circuit and you put the ammeter in that and make sure that it is showing as 1 ampere. Okay. So, you take a known value of current, measure it using the ammeter and make sure that it is reading it as 1. So, then you have calibrated. Suppose the calibration is wrong, okay. You calibrated it, let us say the actual current was 0.9 amperes and you calibrated to measure it as 1, then there is a systematic error. All your measurements will be incorrect. So, that is why the error will be always in the same direction. Your all the actual current was 0.9 amperes, but you have calibrated as 1.0 amperes, right. So, all your measurements will be offset by 0.1 amperes, plus there may be random errors, okay. And if that random error is see, then it will be like this. So, there is a this random is because of the readout error, but this is the actual it's distributed on this average, okay. So, this is 1.0 and this is 0.9, okay. And because there is a shift like this, when you do that take multiple readings and add them and take the average etc., this shift unfortunately will remain, you can't get rid of it, okay. So, you cannot reduce the error by repeated measurements, okay. I hope that point is clear. So, what is calibration? Once again, it is a way to measure a known quantity and adjust the meter, okay. So, for example, if you are using a multimeter, okay, a multimeter can measure many things such as voltage, current, resistance, etc. So, one of the first things that people do when they start using a multimeter is they short the when it is trying to measure the resistance, they try to see what will be the resistance of a short circuit. Okay. It should be 0, but if it is showing 100 ohms, then it is not correctly calibrated. So, you have to adjust there will be a calibration adjustment, you have to use that, so that it will show 0 when you try to measure the short circuit resistance. Okay. All right.